Welcome everyone, and thank you for joining us for today's webinar, GraphRAG Python Package, Accelerate GenAI with Knowledge Graphs. My name is Amanda, and I'm part of the virtual events team here at Neo4j. I'm thrilled to be joined by Zach Blumenfeld, AI ML Product Specialist Machine Learning Engineer, and Estelle Sifo, Machine Learning Engineer. We are super excited to have you all with us today. Just a quick note about questions before we get started. We invite you to submit any questions you have throughout the session using the Questions tab located at the top of your screen. We'll answer as many questions as possible at the end of today's presentation. And if we don't get to them all, someone on the Neo4j team will reach out to you directly, or you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. So with that, I'll go ahead and hand it over to Zach and Estelle.
Awesome. Thank you. Excited to get started today. We have a pretty jam-packed agenda. So I'm going to start with just an overview around GraphRAG and Neo4j. After that, I'm going to cover the GraphRAG Python package at a very high level, at which point I'm going to hand it off to Estelle for a demo. And then we'll finish it off with some resources and next steps for learning. So I think a lot of us are familiar with GenAI at this point, right? We see GenAI applications for knowledge assistance, report generation, search APIs, different chatbots across a ton of different industry verticals. But a lot of the challenge with GenAI comes down to things like lack of domain knowledge inside of the pre-training data, inability to verify or explain answers, especially when working with very domain-specific data and very exact use cases. Also issues with hallucination, and all of this leads to a bunch of ethical and data bias concerns as well. So there's this thing that has been started to become more standardized, which is retrieval augmented generation, or RAG, which many of you are probably already familiar with. And the idea behind RAG is that instead of a user or some service communicating directly with a language model and getting a response back, it instead is going to communicate with this retriever. So sending a question to a retriever, and that retriever is going to query some external database, often proprietary data or some specific type of data, to bring back relevant info, which then gets combined with the question in a prompt, and then the LLM can provide a more complete answer with deeper explainability, right, by using that retrieved relevant information. And so a question often comes up, well, what type of data source is ideal for retrieval augmented generation? And so to think about that, we have to think about the different types of data sources, where our data comes from. And so oftentimes we get a lot of unstructured data. So things like PDF documents, sometimes it's multimodal, like images and stuff like that, in addition to text. And there's a couple different ways that we can deal with that, right? We can vectorize that data, basically enabling us to do different forms of semantic search. We can also extract structured information, different entities and relationships between different entities from that data. And then in addition to unstructured data, there can also be structured data like your operational store relational database, as well as from different types of flat files like CSVs and tables. And then there's semi-structured data, which is like the document stuff that kind of sits in between. And when you think about like the superset of that sort of data, all these different types of data can be ingested and represented inside of a knowledge graph, which makes a knowledge graph a wonderful data representation for AI applications. And we've seen in academic works and other sort of external validations that knowledge graph can help improve the accuracy of LLM responses. In this particular paper, looking at a 3x improvement from using SQL alone. And so when we think about Neo4j and how our graph database is modeled, there's really three important components. There's nodes that represent entities, people, places, and things. And then there's relationships, which are those connections or verbs or actions between those people, places, and things. And both nodes and relationships can have properties. These properties can be strings, they can be dates, they can be sort of long pieces of text, they can be metadata about provenance and source lineage, and we can also put embeddings on there, vectors. which can help us with search. And Neo4j allows for a lot of different types of indices to enable search on this data, in addition to Cypher and some of the graph traversals that you will see later. So that includes full text search. So this is like your Lucene-based sort of tokenized search, vector search with approximate nearest neighbor, range indices, which allow for sort of your standard kind of B tree and normal predicates that you would use for equality and range for numbers and dates. You have geopoint indices, as well as text indices. So all of these things that we can use together with graph traversals to retrieve additional information. And when we think about the sort of value that comes with the Neo4j database for GraphRAG, it really breaks down into kind of three high-level things. One of them is higher accuracy and relevance by being able to provide additional context from a knowledge graph. And the fact that Neo4j is an operational transactional database, which means that you can update your data in real time and make that immediately available for AI models. There's also explainability and governance, fine-grained security controls that will allow different users to only traverse over different information. So the AI model can only access what's appropriate. Explainability through the different knowledge graph relationships, which allows for sort of a very human readable sort of line of lineage of where information came from and how the logic was derived to retrieve information, as well as accelerated development. We have spoken in the past about the large amount of GenAI ecosystem tools that we've created, and we're going to be focusing on that a lot here with the Python package, showing you more tools that you can use to help simplify your workflows. And there's a lot of different GraphRAG patterns that we use to accomplish this. Everything from vector and hybrid search with additional graph traversals for context, which we're going to be focusing a lot on today. But there's other patterns that we may not have time to cover today, including things like text to cipher, which is taking a user question and converting it over into a graph traversal, basically. There's graph vectors, where we can use graph data science to create vectors from structured data in the graph. Graph filtering, so different pre and post filtering patterns that we can use with graph. And of course, all of this can be used in multi-step and agentic workflows as well. So let's talk a little bit about what we're here for today after that overview, which is the GraphRAG Python package itself. So the GraphRAG Python package basically offers you an end-to-end workflow inside of Python to make things a lot simpler to put together for GenAI and knowledge graph development. It's supported by Neo4j, and it basically accelerates going from your PDF document to building your knowledge graph, basically making it GenAI ready with vectors and structured entities, implementing a whole host of useful retrievers that combine things like vector search, hybrid search, text to cipher, different cipher templates for graph traversals, and then having classes where you can create the entire GraphRAG pipeline, including providing prompt templates, leveraging a ton of different language models, and basically putting the whole thing together with much less code than before. And so to give you an idea of what this looks like before we go into a demo, basically I'm going to show you 3 to 4 steps here. So first, you can connect to Neo4j using a driver. It's a pretty simple step once you have your Neo4j database created. Next, to build your knowledge graph, and this is a minimal example, you can define your language model. And we'll be using GPT a lot here, but we'll talk a little bit more about how you can use virtually any language model for this. Same with embeddings. We're going to be using OpenAI's default text embedding ADA, but you can use others. And once you've defined those things, in addition to some optional parameters, such as different text splitters and stuff that you could provide, you basically instantiate this simple KG pipeline, and then you run that pipeline. And once you're able to ingest your documents, you can then create your retrievers. In this case, I'm using a vector retriever, but we'll see there's other sorts of retrievers that are contained inside of the package. And then we create a GraphRAG object down here, providing in an LLM in the retriever. And after that, we can run it. We can provide it a question, and it comes out with a response. And you can integrate this into your knowledge assistant or any other GenAI service that you'd like. So with that introduction, I'm going to pass it off to Estelle for a demo.
Thank you, Zach, for the introduction. So now I'm going to do a small demo about this new Neo4j GraphRAG Python package. And today we will demo how to go from a PDF document to Q&A with your knowledge graph. So for this demo, we are going to use a couple of papers about this disease, lupus. So don't worry, you do not have to understand the field to understand what's coming in the webinar. We are making it very generic. So our goal for this first part is to build the knowledge graph. So basically ingest data into this Neo4j Aura instance that I created earlier that is currently empty. And so for this, we will use this notebook. So I will just run everything while I'm talking. So to run this notebook, you just need a couple of dependencies. The first one is python.env to manage some secrets, Neo4j GraphRAG, the package we're talking about. And in this demo, we are going to use OpenAI for embeddings and the LLM part. So we also need to install the OpenAI package. If we go into the setup, so nothing fancy here. We are just instantiating some variables from the var. And then we define the list of files that we want to process. So in this demo, I'm only selecting one file, which is about biomolecules. And then for our knowledge of builder pipeline, we need to define a few extra variables. One of them is the node labels and the relationship we are interested in, and we will ask the LLM to extract for us. So we have entities, a bit generic, like person, organization, or place, and we have very domain-specific entities. So since we are analyzing papers in the medical field, we have entities such as disease or drug or molecule. And we also define, as I was saying, the type of relation we are interested in. So what kind of relation between these entities we want the LLM to extract for us. Then once we have those, we need to define a few other components. One is the embedding that we want to use. So which kind of embedding will be computed for each of the chunks that will be extracted from our document. And the LLM we want to use for the entity and relation extraction. So today we are going to use OpenAI embeddings and the OpenAI model GPT-4o Mini. In this demo, we also choose to use a custom template for entity and relation extraction. This is not required. You can use the generic one that is provided with the package, but here we choose to tune it to ground it to the field we are studying. So adding some very specific instruction about medicine, basically. And so once you have all these different pieces, you can start building your knowledge graph pipeline. So we instantiate a Neo4j driver, and then we create this object here, simple KG pipeline, where we just pass the driver, the LLM, the embedder, all the entities we're interested in, all the generic and the domain-specific entities, the relationship, and the prompt template. And we also need to specify here that we are processing a PDF file, because we can also process text directly. But when we process PDF, we have an extra step, of course, to extract the text from the PDF. So we need to specify this here in the knowledge graph simple KG pipeline constructor. And so once this we have this object, we just need to call runAsync function with the path of the file that we want to process. So the process is done. So now we can check the result in the Aura DB that we were seeing before. So there should be some data in it now. So you see all the different nodes that were created. Let's start from the documents. So we create a single node for the document where we save the path. And if I expand this one, what you can see is all the chunks that were created from that document. And for each of the chunk, we save the text and the text embedding that was computed with OpenAI. So now if I expand one of the chunks, so here you see all the different entities that were extracted from that chunk, so entities that are mentioned inside the text. And we should also see, so for instance, here you see the relationship between those two entities, which is also something that was extracted from the LLM. So now we have a graph. We imported a PDF, we turned it into a graph. Now the question is, how can we use that to ask questions to the data? So for this next part of the demo, I'm going to use a very similar DB, except that we imported a few more documents. So we imported 3 documents instead of 1. And we tuned a bit the chunk size in order to have smaller chunks and optimize a bit the semantic search and have more specific embeddings, basically. So here we do it in exactly the same way. So we install .env, Neo4j, GraphRAG, and OpenAI. We instantiate our variables and our driver. And the first thing we need to do is to create a vector index so that the embeddings properties on the chunk are indexed. And we can do that using a helper function from the Neo4j GraphRAG package called createVectorIndex, where we just need to specify the driver, the name of the index we want to create, and the label and the name of the property that contains the vector, and the dimension of this vector, and finally the similarity function that will be used to compute the similarity and retrieve the best scoring results. So again, we need to define the embedder. This one has to be the same one we use to embed the chunk text in the ingestion step, in ingestion pipeline, because we will compare the user question to the chunk text through this embedding. So we have to use vectors in the same space. And once we have that, we just import our vector retriever. We instantiate it with the driver, the name of the index, the embedder, and we have optionally, we can specify only the properties that we want the vector, the retriever, to return for us. And in that case, we are only interested in the text property on the chunk. So we just specify it here in the return properties argument. And once we have our retriever, we can actually search the results. So we provide the query text and the number of chunks that we want to retrieve from the vector index. So here we specify top k equal 3. So we are actually getting 3 items as a result. And if we look at those items, you can see that we have the text of the chunks. So this vector retriever is performing only a similarity search on vectors and returning the chunks that match that are the best match for the user question. We can expand on this and go towards a vector cipher retriever. So in the vector cipher retriever, we start again from a semantic search. And then we can append a cipher query to basically traverse the graph around the nodes that have been found to be the best matches. So you can imagine writing any kind of cipher query. You can filter on specific nodes or specific relationship, whatever fits your use case. Here we are using a query which is still quite generic in the sense that we are traversing the graph from the chunk 2 to 3 hops. And we're extracting triplets, so entity, relationship, entity from the domain graph, let's say. So let's see an example. That would be easier. So we have instantiated our vector cipher retriever. We use the same search query with the same query text and the same top K. And we look at the first item, and we are just printing here the part of the context that comes from the text itself. So we just concatenate all the text that comes from the different chunks. And in the context, so we append some relationship information. So we append information like systemis lupus, authored, n.angle. Something, the author of that paper. So we expand the context by adding some information from the graph. And the interesting thing here is that this KG context from relationship does contain information that's not necessarily contained within the chunks, which are here in the text chunk context, because we traverse the relationship, and so we can traverse relationship that comes from maybe another chunk, or another document, or even that is not from a chunk, but that comes from some human knowledge or whatever. So this is the interesting thing in this approach. So now we have seen how we can retrieve information from the graph with retrievers. The next step is to pass this context, this retrieve context, to the LLM for the LLM to generate some answer. And so that's why we have this GraphRAG object here that will do exactly that. So for the GraphRAG object, again, we need an LLM. That can be any LLM, whatever it does. It's absolutely not related to the knowledge graph construction pipeline this time. We could even use some Mistral LLM or whatever. And again, we have the option to provide a custom template if we need to. So we instantiate the vector only GraphRAG and the vector cipher GraphRAG object, and then we will compare the results for a few queries. So the first query is, how is precision medicine applied to lupus? So this query is, I would say, simple in the sense that it's the topic of one of the papers I've shown you before. So you can imagine that it will be pretty easy for a vector search to find the answer, because it's probably contained in one, or let's say a few chunks. And so we will be able to provide a context that contains all the relevant information to the LLM. And this is what we see here. The vector response and the vector plus cipher responses are almost identical. So this is expected. Now we are going to study a slightly more complex questions, because it involves information that comes from different papers, maybe many different places in the paper. So the question is, what are the most frequent symptoms of lupus, and why is it difficult to diagnose? So again, we do the same query for vector RAG and vector cipher RAG. And here, this time you see that the results are very different. So for the vector response, we have a few answers, so a few symptoms and a few ideas about why it's difficult to diagnose. But when we look at the vector plus cipher response, we have much more possible symptoms, maybe more detailed. And the reason is we have this relation triplet at the end of the context that encompass information from other chunks, other documents. So this is why the vector plus cipher is super useful and can help you in improving the performance of your RAG and GraphRAG. So before closing the demo, there is one last thing we want to show you. This is called the hybrid retrievers. So so far we have only used semantic similarity of text to search for the chunks, which means that, for instance, a chunk mentioning disease or illness will probably be retrieved together because those words have the same semantic meaning. but we are not leveraging at all the full text index that Neo4j also supports. And that's what the hybrid retriever is doing. So it's searching both in the vector index and in the full text index, is normalizing the score, re-ranking the result, and basically returning only the top K based on those two indexes. So you may have relevant information coming from the full text index and relevant information coming from the vector index. And the way you do that, so first, you need to create a full text index if it doesn't exist already in your database. So we also have a helper function for that. Similarly to the create vector index, you need the driver, you need the name of the index you want to create, and the node label and the properties that will be indexed. And so once you have that, you can instantiate your hybrid retriever with your driver again, the name of the vector index, the name of the full text index, and if needed, the embedder and the return properties. And then you use it exactly in the same way. They have, all the retrievers have the same search interface. So you provide your query text and you basically see the results. So this is not in this demo, but I just want to mention that we also have a hybrid cipher retriever that works in the same way as the vector cipher retriever, which means that once you have your chunks identified through the vector index or the full text index, you can expand and traverse the graph and extract more information and provide this information to the context in the LLM. So that's it for the demo. Thank you for following here. And back to you, Zach, for the conclusion. Thank you.
So as some follow-up resources, and don't worry, we'll pass these slides out. So if you don't get like a screenshot of the URLs, you will get them later. We have a link to the demo code here, going over what Estelle just covered. There's also a great new free course on Graph Academy. And actually, I can show you that right now. So this Graph Academy course will walk you through multiple steps. It's like a free online self-paced course going through creating embeddings, creating the knowledge graph, using different forms of vector and hybrid retrieval if you want a more sort of in-depth learning experience. We also have the docs, which are linked on the page. And these docs will go into, for example, if I go to RAG, it'll cover all the different forms of RAG pipelines you can use here, retrieval classes you can use, as well as cover like different prompt configurations and being able to use custom models, different models from LangChain, Vertex AI, Azure OpenAI, etc. There's also other resources here for our website, which includes other learning materials for GenAI and ecosystem tools, other ecosystem tools that we have in general, upcoming events, both live and webinars. And then for more in-depth posts, you may have already read our GraphRAG Python package post, which goes over a very similar example to the one Estelle just showed you. And then we have a few other examples as well that go over, for example, using structured data, importing structured data, and getting started with that in the GraphRAG Python package, along with a little bit more depth on vector and cipher and hybrid retrieval. So with that, I think we can open it up to Q&A.
All right. Well, thank you, Zach and Estelle, for such a great presentation. We did have some time for a few questions. I wanted to remind the audience, if they'd like to submit a question, they can do so by typing into the questions tab at the top of your screen. If we don't get to them all, someone on the Neo4j team will reach out to you directly, or you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. So I'm going to go through some of the questions that we got during the presentation. All right, this first question, what models can I use with this?
So actually, Estelle, maybe I should hand that one over to you to cover that in depth.
Yeah, sure. So in the demo, we used OpenAI models. We also support OpenAI on Azure, and we support other providers. So if I'm not forgetting anyone, we are supporting Vertex AI, Mistral, Anthropic models like Claude, Cohere, and you can also use a local model with Ollama.
Awesome. Thank you for that. All right, moving on to the next question. Can I use Neo4j with a vector database?
And Estelle, you can take that one too if you'd like.
So the answer is yes, in the sense that in the package we have some specific retrievers that work if your vectors are stored in a vector database. So at the moment we support 3 vector databases, VV8, Pinecone, and Quadrant. And so you can have a retriever that will just perform the semantic search on the vector database and do the graph part on Neo4j.
Awesome. Thank you. All right, moving on to the next question. Is there a link to the notebook code?
Yes. So I can take that one. The demo code is going to be at this link. And again, if you don't get a screenshot of it or something, we'll send these slides out afterwards. So you'll be able to get these via email. But that should give you everything to replicate what we're doing. Also wanted to mention, you do need to start a Neo4j database for this to work. So we didn't go over all of that in the example, but we'll have directions in there. So basically you can either use Aura free, which is our fully managed cloud service offering. You can also use a pro free trial or a professional, which will give you a little bit more memory. It might be a little bit more of a better experience there, given that we're using a lot of vectors. So the short answer is yes, and it is at that first link.
Thank you, Zach. And it looks like we have time for a few more questions. This individual is asking, what other kinds of retrievers do you have?
Estelle, I don't know if you want to take that one as well.
Yeah, again, so in the demo, we demonstrate the vector cipher, and hybrid retrievers. We mentioned hybrid cipher retriever. In a previous question, we also talked about the external vector retrievers, so the retrievers with vector database. And the last retriever that we support is text-to-cipher retriever, where instead of performing some similarity search on vectors or text, you're trying to translate the user question into a cipher query directly to really extract the specific information that's needed to answer your question. Yeah, the list is here. Thank you, Zach.
Thanks, Estelle. And then the next question, can I use this with LangChain? Hopefully I pronounced that right.
Yes, LangChain. So you can't use our retriever within a chain in LangChain. They do not use the same interface. However, there are some parts of LangChain, like the LLMs, that you can use within our package. So for instance, if we do not have implementation for the model you want to use, you can open an issue in our GitHub so that we know you are interested in that model. And in the meantime, you can use the implementation in LangChain if there is such an implementation.
Awesome. All right, now wrapping up, it looks like we have time for one more question today. So we will end with this. When do I use this versus LangChain or Llama Index?
Yep. So I'll try to take a crack at that one, and then Estelle, you can come in and add feedback to this too. So one of the benefits of this Python package is that it gives you a pretty good end-to-end, starting from building the knowledge graph all the way to retrieval. We have ecosystem integrations inside of LangChain and Llama Index to do similar things. But the nice thing about this package is that it gives you these preset patterns, particularly in the knowledge graph retrieval patterns that we were talking about earlier, which can simplify the development experience a little bit. So you can go either way. This package just sort of offers a little bit more convenience on the retrieval side and connecting that to the knowledge graph building component. And I don't know, Estelle, if there's any more that you'd like to add to that.
Yeah, I would just add that at the moment, the long chain or Llama Index implementation are community driven, while our package is a real product from Neo4j. So that's one of the main differences.
Awesome. Well, thank you so much, Zach and Estelle, for being with us today. And for those in the audience, thank you for joining us today as well. I wish you all a great day. Thanks so much.